Hi there everybody, this is Mr. Pope from Winter Grammar School for Boys, and this is the second session that I've done so far. And as you can tell from the little schedule that I've had all linked up on Google Classroom, I've decided to lump geometry and vectors together. And you're probably thinking, why is it that vectors are getting extra special notice? And that's because, maybe not so much at school, but definitely at degree level and beyond, vectors are a significantly substantial area of maths, and unfortunately it's one of those things that you have to have, I feel anyway, a high level of mental imagery of what's going on with a concept, or at the least your algebra has to be pretty spot on. I think vectors are underplayed at GCSE, and I think for the normal A-level maths course actually has been taken a step back. I mean, in the old specification pre-2017, you used to be able to solve problems involving the dot product, various geometric problems, and you can argue that that's been replaced with kinematic problems, speed, distance, time, acceleration, that kind of thing. I kind of feel like they've deviated a little bit from pure mathematics side of dot product, solving things geometrically and just basic vector arithmetic and operations in general. I often find that when I'm tutoring people for STEP, the entrance examination paper for Cambridge and other universities like Warwick and Imperial, when they have mathematics course offers, generally speaking, the vectors questions I feel get a bit of a bad rep. I mean, the very limited, maybe 30 or 40 students I've ever tutored tend to veer away from it, and a lot of the time I've had to spend a lot of work getting them up to scratch with vectors, because I feel there's easy marks there for conceptually very little work, just a lot of intellectually heavy lifting. So anyway, let's just crack into it. So first of all, let's talk about the difference between a vector and a scalar. Okay. So a vector essentially has a magnitude, which is a posh way of saying a value. That's terrible. A value. And it has a direction, an orientation, a way it's going. And this isn't confined to 2 dimensions. It could be 1 dimension, could be 2 dimensions, 3 dimensions, any n dimensions you want. I'm not really going to be talking about non-integer dimensions as such. 1, because my knowledge on that is pretty limited, and 2, that's definitely beyond first, second year degree level courses for mathematics. Well, maybe it isn't, maybe times have changed. But I think for 14, 15, 16, 17-year-old mathematicians it might be a bit early. I don't know. And what's the difference between that and a scalar? Well, a scalar is just a quantity or something that has magnitude. So let's have an example of both. You could have a vector which is just 1, which means if I'm on a real number line and if I start at the origin, I just move a length of 1 to the right in the positive direction. Whereas, confusingly, I could just have a scalar, it's just 1, i.e. I've got 1 of something. I've got 1 square. It's more of a counting thing rather than an amount and a direction of movement. We're going to be looking at the 2-dimensional case. So what do I mean by that? Well, first of all, let's reacquaint ourselves. You've probably been told about this at school, but we're going to be working in the Cartesian plane, however you want to pronounce that. And pretty much the x-axis runs in the positive from left to right, and the y-axis runs from down below up above, like that. So there's various ways of defining vectors, and we're going to be going over a couple today. But one way of defining vectors you might have seen at school is that we have something called a column vector. Now I'm just going to write col with an underlined M just to save time. And suppose I'm interested in the vector that goes 3 to the right and 4 up from the origin, so it's looking like that. The way I would write this is 3, 4, and you need to get it in your head that it's x and then y, and the way I like to think about it is alphabetical from top going downwards. So the vector 3, 4 just means you start at the beginning, you go 3 to the right, 4 up, and that's your end point. You draw a straight line. Okay, now there's some fairly there's some interesting things with vectors. Let's talk about some operations with them, some really simple operations first, and then we'll look at some consequences. So you can think of vectors as just a list of numbers that tells you instructions. And let's have a look at a couple of operators. So let's say I've got the vector AB, which means I go A to the right and B up, and I'm going to add on another vector, let's say CD, which means I go C to the right and D up. So what does that mean? Well, it means I've got one vector, which I'll call going A along like this and B up. So it's going to look like this. It's an arrow like that. And then I add the CD vector, which is C along and D up, say, like so. And I put that tail on the end of it like so. And now I'm claiming the net result, and let's deal with this. So there's the purple one. I'm saying the net result is just if you were to add them row by row. So on the top row, you've got A add C, which is A plus C, and on the bottom row, you've got B plus D, which is B plus D. And I'm saying that red vector is the same as if we started at the beginning and ended at the end, like so. And that vector is A plus C, B plus D, like so. And if you think about it, that kind of makes sense because the total going to the right is A, and then C, because this part is C from here to here. And then going up, you've got B, which is there, and then you've got a D, which is here. So yeah, you do have A plus C, and then B plus D going up. So hopefully geometrically that makes sense to you. And essentially it doesn't matter if I added or subtracted these two vectors. It would just mean you'd be adding or subtracting the two components. And essentially you do it row by row, and you can do that as much as you want. That's totally fine. However, there's some really weird consequence that from if you're thinking about it. Look, and this is what I mean. Let's suppose I've got A, B, and now let's say I've got plus CD, and now let's say I've got plus minus C plus E, and now let's say I've got plus C minus E. So what would that give? Well, you've got an A there, the C and minus C would cancel, you've got another C there, so you're just going to be left with AC, A plus C. And on the bottom, you've got a B there, the E and minus E cancel, and you've got D, so it's B plus D. Oh, hold on a minute, what's going on here? You've got lots of vectors going on. Well, let's draw some diagrams. If I've got A, B, like so, that's my AB, and then I've got CD, which again is CD, something like that maybe. And now, what am I doing? I'm minusing C, so I'm going back C, but let's say I'm going up E. So now that vector's going like this. So that's back C, so minus C, but then up E. And then I've got to add a C and minus E. Well, what happens there? I go along C and down E, so I'm going back along itself. And notice how I end on that same place as if I'd gone A plus C and B plus D. Sorry, that should have been a D. Yeah, it's really bizarre. So what's important is this thing here. We could call that lots of things, but generally it's called the resultant vector. It's the end result. Okay, and the key points about vectors is the only thing that matters is the start position and the finish position. It doesn't matter if I define a vector as A plus C and B plus D, I start here and end there, and that is the exact same result in vector form if I do all this business and I'm going all around the houses, as long as I end up boop at the end like that. It's really bizarre, so let me rub this out. What I'm claiming in vector form is it doesn't matter how much you add or subtract. In vector form, going from here to here is the same as from here, like that, as long as you start and finish at the same place. And the reason for that is because you can add and subtract the individual vector component parts. And just like when you're adding and subtracting lots of positive and negative numbers, they all cancel out in the end. So that's a real important thing. And the end result is literally called the resultant of that vector, or just the resultant vector. That's going to be a really key point. So adding and subtracting vectors, interesting properties. As long as you get that in, that's pretty much the key concept of it. Now, in terms of GCSE, when it comes to multiplying vectors, interesting. Well, there's various ways of multiplying vectors, but at GCSE you're only ever told about one way, and that is if I've got a vector, let's say, okay, now we want to multiply. So this was addition and subtraction. Oops. And this was multiplying and division. But there's a bit of a caveat there. See, in mathematics, the only way you can divide vectors is when you're dividing and multiplying by a scalar. Okay, a constant. Okay, scalar or a constant of value. Okay, so what do I mean by that? Well, because if I have, say, the vector 2, 1, if I times that whole vector by 3, that will just become 3 times 2 times 3 times 1 on the bottom, which will be 6 over 3. Please notice how this works, and what's going on here is this part is the vector, and I'm multiplying it by the scalar, which is 3. Similarly, if I wanted to divide by a scalar, that's the same. Say I wanted to divide by 3 instead, well, that's the same as timesing by a third. So you're not really dividing, you're just timesing by what's called the multiplicative inverse. Okay, so timesing by 3, and dividing by 3 are opposites, they're inverse operations, and dividing by 3 is the same as timesing by 1/3, and we describe 1/3 as the multiplicative inverse of 3, because if I times something by 3, you've got to think, okay, what have I got to multiply that result by to get back to where I was, and that's clearly a third. Anyway, so, and then this shouldn't pose too much of a threat either. This is going to be a third times 2, and this is going to be a third times 1. And don't be afraid to have fractions inside your vector. So that'll be 2/3, 1/3, like so. Okay, so there's a little bit of a caveat here. Multiplying and dividing by scalars, pretty much how you'd expect it to be. That's totally fine. However, if I was to say something like 2, 1, this vector, and I wanted to multiply it by this vector 3, 2, well, it doesn't work as how you'd expect. Okay, it's not, and I repeat, it's not 2 times 3, which is 6, and 1 times 2, which is 2. Okay, you can't just multiply vectors like that. And similarly, you can't divide by vectors like that either. We're going to be covering how you multiply vectors together. Okay, and there's two main ways. That's called the vector product and the scalar product. But for now, for this session, multiplying and dividing by a scalar is pretty much it. Okay, so let's have a look here. Let's have a look at some implications of multiplying and dividing by a scalar. Well, let's suppose I do have that vector 2, 1. So there you go. 2 along and 1 up. There's my sorry little vector I had originally. Now what does 6, 3 look like? Well, that's going to be going 1, 2, 3, 4, 5, 6, and 3 up, 1, 2, 3. And if I've done this right, something like that. So it's 3 along, 6 like that. Okay, what can you infer what's going on? Well, in actual fact, whenever a vector, let's say 2, 1, has a multiple in front of it, this is parallel to 2, 1 as well, i.e. when vectors are multiples of each other, and what we call, if they are scalar multiples, i.e. you've just multiplied by a single value, if they're scalar multiples of each other, then they're parallel. That means they run in the same direction. That's really important. Okay, is that always true? Well, surely multiplying by fractions and positive numbers fine, but what happens with negative numbers? Well, let's say I had -1 times by 2, 1. Well, let's pick different vectors. Let's say 3, 5. Let's have -3, 5. So -1 times -3 is +3, -1 times 5 is -5. So what's going to happen here is I've got the original vector, -3, 5, which is 1, 2, 3 back and 1, 2, 3, 4, 5 high. So there it is. And I have this now new vector 3 minus 5. What do you think is going to happen there? Well, I go along 3. 1, 2, 3, and I go down 5 this time. What can you tell me is the relationship with these two vectors? Well, we've already said that if they're multiples of each other, then they're parallel. So if this is parallel with this, then they're on the straight line. But what's happened? If k is less than 0, then the direction has reversed. Okay, so when you multiply a vector by a negative number, you're essentially doing the reverse. It's the reverse of that vector. It's going in the opposite direction. Okay. Now, sometimes in GCSE maths, they like to get a little bit cute. What do I mean by that? Well, they don't even use numbers, and that's a perfectly valid strategy. So what do they mean by that? Let's say I've got a coordinate system grid, kind of, something like this. Let's say I've got a grid that's made up of lots and lots. You have to excuse my drawing here. Let's say I've got a grid that's made up of lots and lots and lots of parallelograms. Identical parallelograms, I should have said. So I've got a grid that's made up of identical parallelograms like so. And the distances between all of the intersections of the lines are the same. So if this is the origin, we'll call this A, B, C, D, point E, F, G, H, I, J, K, M, N, not O, P, Q, R, S, T. Okay, now there's different ways of defining vectors, as I said before. Let's define a different way. Let's say the following. If I have one letter, O to E, and that's telling me the instructions. The arrow saying going from one to another, O to E, from left to right, we'll call that vector little a, with a little line under it to denote a vector. Now, this is really important. In some textbooks, they'll just have a bold A looking like that, or you could just have a regular A with a line under it. Generally speaking, that's just to denote that you're working with vectors. And to be honest, you don't even have to write the line under it. As long as you're aware and you keep track that A is not a variable, it's a vector. So what we're saying is from O to A like that. That is, it's O to E, the vector is A. And now let's define a different vector. Confusingly, from O to A, let's call that the vector B. So this is B. That was terrible. From there to there. That's B. Okay, so let's suppose I want to work out how do I get from O to M. Okay, now what did we say before? We said when you're adding vectors, or you're putting them together, it's only the start and the finish point that matter. So I can go all around the houses. I want O to M. So the immediate first choice is I need a vector that goes from O to M, looks like that. Whoops. From O to M, looks like this. That is the vector, or the resultant of O to M. But there's various ways I could have done this. For example, I could have gone up to, and then along 1, 2, 3, and that would have been the same result. Or I could have tried a combination of saying up 1, along 1, 2, 3, 4, and then up 1, and then back 1, and that end result would have been fine. So really, we can get from O to M via a combination of our vectors we defined already. So let's just cut to the chase. I've got 1, 2 places to go up to get parallel with it. So that'll be 2 lots of A plus 1, 2, 3B. 3B. And I can define O to M as just the addition of 2 vectors like so. Notice if I'd overshot it like I did in the previous example. Let's count it together. I've got an A plus an A. Well, no, I've got an A. So there's an A. And then I've got 1, 2, 3, 4B. So I've got a 4B. And then I've got another A. So that's an A. And now because I've gone backwards, I've now got a minus B. And hopefully you can convince yourself you've got an A there and an A there, which is 2A. And you've got 4B minus a B, which will give a 3B. Okay. So, yeah, that seems pretty good. So sometimes two-dimensional vectors are given as column vectors like numbers. Other times they can just be written as abstract quantities in terms of letters. And don't beat yourself up about knowing what the exact numerical value are when they are letters. Just work with them, and just I think the easiest way I can explain it is you just treat them as building blocks where you can add multiples of one to the other. If you want to go reverse the direction of one, you just make it negative and so on. Now I've got a couple of examples. They should be fairly easy. If you want to pause the video, be my guest and have a go. So two vectors A and B are shown on the 1 centimetre grid below. Show that the vector A plus 2B has a length of 7. Okay, so give it a whirl. I'll do it in a second. Okay, so let's think about it. What is A? A is the column vector of, well, I go 1, 2, 3, 4 to the right, so 4 and up 1. Notice how the arrow is starting here and it's going along this direction, ending there. And if I look at B, well, what is B? B is back 1, 2, so it's minus 2 in the x direction. Should put an equals there, and it's up 1, 2, 3. So now I have the vectors A and B. Let's think carefully what A plus 2B is. Well, that's A, which is 4, 1, plus 2 lots of minus 2, 3. So let's do it row by row. I've got 4 plus 2 lots of minus 2. Well, 4 plus 2 lots of minus 2 is 4 minus 4, which is a fat 0. Now if I look at the bottom row, I've got 1 plus 2 lots of 3. And 1 plus 2 lots of 3 is 1 plus 6, which is 7. So actually the resultant of this is just the vector 0 along and 1, 2, 3, 4, 5, 6, 7. So yes, that is indeed 7 centimetres long because we're working on a 7 centimetre grid. Yep, seems fairly easy. Okay, next question. O to A is 2 lots of A and O to B is 3 lots of B. Point P is on the point AB, so P is somewhere on this line here, such that A to P and P to B is 3 to 2. Interesting, so P is here such that for every 3 parts of this, there's 2 parts of this. So another way of looking at this is it depends how good your ratios are. If it's in the ratio of 3 to 2, then that's 3/5 to 2/5. I add the 3 and 2 together, so that means 3/5 of the total distance of A to B is A to P, and 2/5 of the total distance of A to B is P to B. Okay. The question is asking me to show that O to P is sum K times by 4A plus 9B. What's the value of K? Okay, so what am I trying to do? I'm trying to go from O to P, like so, like that. Now there's multiple ways you could do this. You could either go from O to A and then A to P, which is perfectly acceptable, or you might want to go from O to B and then back up B to P. And the way I like to do this is I like to write out a little story of what I'm doing. So if I'm going from O to P, that's the same as O to A. So O to P is I'm going from O to A, and then I'm going from A to P. Notice how, like, when letters are next to each other like this, they almost cancel out and I'm left with O to P. Remember, it's the start and the finish that matter. So do we know, okay, so O to P is here. Do we know what O to A is? Yes, it's 2 lots of A. That's easy. Plus, do we know what A to P is? No, but we know it's 3/5. It's 3/5 of A to B. Sidebar. Let's think about what A to B is for a second. Well, I want to go from A to B. But I think to do that, I'm going to have to go from A back to O and then O to B, like so. So, A to B is the same as A to O plus O to B. Now what is A to O? Well, that's just back down again, which is going to be negative 2A and then O to B is just 3B. So actually O to P is 2A plus 3/5 of, and now I know what to substitute in for A to B, and that's this thing. I'll slide it in there. Okay, I think I'm ready to go now. So let's think about it. I've got 2A here, and I've got 3/5 times minus 2A. So that's minus 6/5. So 2 is 10/5 in my head. Minus 6/5, that's going to be 4/5 of A. Plus, and 3/5 times 3 is going to be 9/5 of B. So question, what do these two terms have in common? Well, they both have a fifth in common, so that's 4A plus 9B. So O to P in factorised form is 1/5 of 4A plus 9B. And look, we've got 4A plus 9B, so K must be the same as 1/5. So there it is, K is 1/5. Okay, right. Moving on. You want to pause the video and have a go for yourself. And I'm going to go through it. So A, B, C, D, E, F is a regular hexagon with centre O. O to A is A, O to B is B, M is the midpoint of BC, and X is the point on AB extended, such that AB, BX is 3 to 2. Prove that E to M to X are on a straight line. Okay, let's digest this bit first. X is the point on AB extended. So let's extend AB. So all I'm doing is taking the line AB and I'm making it longer. And A to B, B to X is 3 to 2. So if this is 3 parts, then I go 2 parts this way and X is somewhere over here. Now apparently E, M, X are on a straight line. So if I draw a line from E through M through X, apparently that's a straight line. So I need to prove that that's the case. So just like before, if I've got things in parts, then if AX is the whole thing, that means A to B is 3/5 of A to X, and B to X is 2/5 of A to X. I can split it up into chunks. Okay. Now, let's think. How am I going to get from, let's say, E to M? Right, I've got 1, 2, 3 points. Let's try and connect up any point on the orange line, just to see. So how am I going to do that? Well, I know how to, let's think about it. I go, well, what's the quicker way? I think if I was to go around the hexagon, it would be E to D, then D to C, then C to M. I think that would be the quickest way. I mean, I could go around the other way, or I could just go around the edge of the hexagon. I think it'd be quicker to go anti-clockwise. So it's just E to D plus D to C plus C to M. Okay, what is E to D? Well, E to D, there, is the same as A to B because they're parallel, and A to B is the same as down, up, like that, because it's the start-finish point. So I need a minus A plus B. So E to D is just minus A plus B. D to C, well, this is the same length and parallel to this thing, so that's just going to be plus B. And then finally, C to M, because it's the midpoint of BC, it's just going to be half of this parallel line here, because it's the same, because C to B is the same length as O to A, because they're hexagons. So this is going to be just plus a half of A. If I tidy all this up, what do I get? I've got a minus A there, plus half an A there is minus half of an A. And I've got B plus a B there, so it's going to be plus 2B. Okay, I now have E to M is minus half a plus 2b. Okay, right, what shall we try now? Well, how about we try to work out of those 3 points, e, m and x, what's another good combination? Well, let's try, we've got mx or e to the x, so let's try ex. How do we get from e to the x? Well, I'm going to do a similar approach. I'm going to go e to d, d to c, c to b this time, and now b to x like that. That's perfectly valid. The start and finish points are both e and x. That's totally fine. So notice that it's just e to m, which we know already, plus m to b, plus b to x. And the beautiful thing about doing it that way is I can save a lot of work, because e to m is already in there, which is a half a plus 2b. M to b, if you think about it, is the other half of a, so that's plus a half a there. And b to x, if you think about it, b to x, well, if a to b is, what is it, minus a plus b, then how do I go from 3/5 to 2/5? Well, what do? I divide by 3 and then times by 2. So it's actually 2/3 of minus a plus b. Whoa, got some fraction things going on here. So what is e to x? Well, the half a's they cancel, so I've actually got minus 2/3 of a from this thing here. Okay, plus, now what's 2b plus 2/3 of b? Well, 2b is 6/3 plus another 2/3 is 8/3 of b. And now I can take out a factor. So what have I got here? Well, I can actually, if you think about it very carefully, I want it to be a multiple of minus half a plus 2b. So think about it. If I take out 2/3, so that's 2/3, and this will be minus a plus 4b, I need to divide this side by 2, so that needs to be a 4/3. So if I make this a minus half a, and this becomes a 2b, then this needs to be a 4/3, and then that works out. Because 4/3 times minus a half is 2 minus 2/3, and 4/3 of 2 is 8/3. And now look, e to the x, or rather e to x, is just 4/3 of e to m, i.e. it's in the ratio of this part is 3 and this part is 1. I've got to go 1 1/3 of e to m as I do to get from e to x. So that means they're parallel. So they're parallel, they're parallel, and they share the same point. So they must lie on the same line. They are what's called collinear. Collinear. Now my spelling of this always gets me up. I can never remember if it's 2 L's or not. It is 2 L's. It's collinear. Okay, if multiple points lie on the same line, they are called collinear. Okay, so that pretty much concludes all the GCSE component of vectors I wanted to talk about. Now I want to start talking about a little bit more of a sophistication. Now, what do I mean by that? Well, we've talked about column vectors where we've got 2, 1, for example, where that means I go 2 to the right and I go 1 upwards, like it's a set of instructions. We've also talked about abstract things where we let, say, from O to X be the vector A, for example, or in this case we might want to call it X, like that. This is more of an abstract form of vectors. The final thing I want to talk about is we're going to introduce something called a unit vector. Now, what do I mean by that? So let's say I've got the XY plane here. And let's say I've got this point here, which is A, and that's the origin. And to get from O to A like that, let's say I do actually have to go 2 to the right. And this is not to scale, this is 1 up in the air. So in actual fact, what's going on here is this is the vector O to A. Now we could write it as the column vector 2, 1, but another way of writing it is calling it 2i plus a single 1j. Okay. Now, what are these i's and j's? I is the unit vector in the x direction. Each of these things is worth 1 lots of I. This is not to be confused with I being the square root of -1. Just I just means a single unit vector in the x direction. And j is a unit vector in the y direction. Okay, it's just a different way of doing things. And then rather unimaginatively, when we look at 3 dimensions later, I is for x, j is for y, and when we're in the 3rd dimension z, we'll use k as the unit vector for z. We won't do any 3-dimensional stuff just yet, that's for another time if you want to check out the schedule. But essentially, if you've got 2 dimensions down, 3 dimensions aren't that difficult. They follow the same kind of rules, and you can probably intuit most of what's going on. The only thing that's a little bit different here is now, I think the more sophistication is suppose I've got the vector O to A, and it's 2i plus j. Okay, now what we talked about in the pure stuff is we talked about this thing called the modulus, or what's called the magnitude. Okay, and it's the absolute length or value of the vector. So if I had mod of OA, is how we'd say it, or the magnitude of OA, essentially what we're trying to say is this modulus of OA is the total length of the vector. And that's quite easy when you think about it, because essentially what's going on here is we've got a triangle with a base of 2 and a height of 1. It's a right-angled triangle because x and y are perpendicular to each other. So all we need to do is the square root of 1 squared plus another squared. And you can tell quite quickly that this is just going to be the square root of 5. So this is what we're talking about when we want the length or the magnitude of a vector. Okay, and just like in the complex stuff, you might be asked for the argument. Or you might be asked for the vector as a bearing. Okay, and oops, that's terrible. And there's no shortcut to this. The only thing you have to be really careful of is using very basic trig. For example, so, ca, toa. So what does that mean? It means sine of an angle for a right angle triangle. So if we call this angle theta. That's the opposite side divided by the hypotenuse. Cosine of that angle is adjacent over hypotenuse, and tan of that angle, the tangent of that angle, is opposite over adjacent. And you know, you should be pretty familiar with this kind of stuff. It's more of a thought bubble. So let's say I was interested in the bearing of the vector O to A. Okay, what is the bearing? Well, if I unclutter this a little bit, what is the bearing of O to A? Well, the bearing of O to A is, if we're facing north, which we'll assume to be this way, it is the angle here, theta, as a 3-digit number of what's going on here. Well, that's fairly easy to compute, because if I look at this triangle, this right angle triangle here, then by alternate angles, that north, the hypotenuse, and that side there, we will form alternate angles. So this is also theta here. This was 1 by a diagram, this was 2. So clearly tan of theta is opposite, which is 2, over hypotenuse, which is 1. So the angle is just going to be inverse tan of 2 over 1. Now you can either leave your answer in degrees or radians. I really don't care. The point is you should be able to calculate basic angles by applying inverse trigonometric functions. And that's pretty much it, really. You need to be able to find the absolute length of vectors. You need to not be afraid about finding angles where vectors join up or make with either the x-axis or y-axis. And really, 99% of problems that you're going to be running into can be solved if you just draw a really nice, clear sketch. And if you've got good mental imagery techniques, you can understand exactly what's going on. You can apply simple angle facts like alternate angles, corresponding angles, interior angles, angles of a straight line, all those stuffs that you should have been going through in 7, 8 and 9, year 7, 8 and 9. So anyway, I'm just going to finish off with a couple of examples. I know yesterday's video was pretty long. I'll try and keep this one under an hour. So I've got a couple of examples. Let's just go through it. So if you want to have a go at this, pause the video now. Otherwise I'm going to go through it. Okay, given that the point A has position vector 4i minus 5j and the point B has position vector minus 5i minus 2j, find the vector A to B. Okay, multiple ways of doing this. Essentially, I like to think of it as I'm at 4i and I want to get to minus 5i, so that's minus 9i. So let's write that properly. It's minus 9i. And I'm at minus 5j with A, and I want to get to B, which is minus 2j, so minus 5j to minus 2j means we're at plus 3j. So it's only 2 marks, it's pretty simple like that, it's not that big of a deal. Find the length of A to B, give your answer simplified third. Okay, so let's have a look at this thing, let's draw a sketch. So here's the origin, say, minus 9i means I go back 9 in the x direction, and 3j means I go up 3 in the y direction. So there's my vector A to B. And if you like, this is A and this is B. So how do we find the length, the magnitude, the modulus? Well, we're going to have to do Pythagoras. So it's going to be 3 squared plus 9 squared square rooted. And this appears to be 9 plus 81, which is root 90. Which I believe is 3 root 10. Now we've covered simplifying surds, and that shouldn't be too much of a problem for you, because root 90 is root 9 times root 10, and root 9 is just 3. So the answer as a simplified surd is just 3 root 10. Okay, next question, bit tricky. Pause the video, have a think about what's going on. I'll go through it in a second. Okay, 2 non-zero vectors A and B are such that if you take the length of A plus B, that's the same as the length of A plus the same as the length of B. Explain geometrically the significance of this statement. Okay, so what's going on here? Let's say I've got the vector A, which let's say is a vector going like this. There's my vector A. And let's suppose B is some other non-zero vector, i.e. actually travels in a direction, and let's say it's not parallel to B, not parallel to A, so it's looking like this. Then what does the vector A plus B look like? Well, you start at the beginning of A and you end at the end of B like that. Now what is this saying? This is saying that the length of A plus B, which is this one, is the same as the length of A, which is this, plus the length of B, which is that. Now, you can clearly see that something's not right here, because if you were to actually walk this distance, if you was to start here at this point and to finish at this point over here, then what would be the quickest, if you walked at the same speed, what would be the shorter journey? It would clearly be the straight line. You wouldn't want to deviate by going along here and then along there. So can you imagine twisting and turning these vectors that are the same length? Well, they're only the same length if A and B are parallel. i.e., I go from there to there, that's A, and then let's say B is not the same length, but it's parallel, B, and then the length of A to B is just that length, which is the same as the length of A plus the length of B. And because they're parallel, it just all adds up. So the only way this is going to work, the geometric significance of this, is if A and B are parallel. Well, it was 1 mark, it shouldn't have been that difficult. Anyway, two different vectors, m and n, are such that the length of m is 3, and m minus n is, the length of that is 6. The angle between vector m and the vector n is 30 degrees. Find the angle between vector m and the vector m minus n, given your answer in degrees to 1 decimal place. Okay, let's think about this. Let's say I've got an origin like so. And let's say I'm going to m, there it is, like that. And there is m, and that's of length 3. Now, what would m minus n even look like? Well, that would be the same, would it not, as minus n plus m. So, another way of looking at it is, if there's another vector over here, where this is n, minus n would be going back along n and then plussing m. Right? If we say this is the little m vector and this is little m, then if n is that way and m is that way, then n minus m would be doing that. And what does that mean? It means that's little m, this little n, then it's saying the distance minus n plus m there, that triangle is 6. Ooh. So if that length is 3 and that length is 6, and I've defined O to n as n and O to m as m, then the length of m, which is just the length of O to m, is 3, as described by the diagram, and n to m, which is minus n plus m, the length of that and the length of that, which is the orange bit, is 6. I think I've built up a good picture of what's going on. And essentially with vectors, that's like the main thing of this. It's like you've got to be able to construct an image of what's going on. And there's no shortcut to it, it just takes practice. And it says the angle between vectors m and n is 30. Ooh, so it's saying this angle is 30 degrees. Interesting. Find the angle between vector m and the vector m minus n. So this vector here is the m minus n vector. Given your answer in degrees to 1 decimal place. Ooh, so it wants this angle. Let's call it theta. Okay. So, what's going to happen here? Let's draw this out without all the stuff. So I've got a triangle like so. Oops. I've got a triangle like so, where this is 6, this is 30 degrees. I want this angle, and this angle's 3. Okay. Is there a way of working out what that angle is? Well, what else can we say? Well, this angle here, if you think about it, is 150 degrees minus theta. Is there any way of working out? No, there isn't. this length here x? Well, no. Okay, now we haven't covered this yet, but it is in GCSE and you should be fairly familiar with it, and that is the sine rule. And for any triangle, if I have this triangle here, let's say that's angle A, that's angle B, that's angle C, and the opposite side is A, the opposite side is B, the opposite side is C, then the identity is that sine of little a over capital A is the same as sine of B over capital B is the sine of little c over capital C. And the inverse of this identity works as well, i.e. A over sine A equals B over sine B equals C over sine C. Okay, so let's deal with this. Do we have an angle and an opposite side? Yes, so we know that sine of 30 degrees over 6 is the same as. Now, do we have another pair of angles and opposite sides? Well, we've got this 150 minus theta and 3. So we're going to have sine of 150 minus theta all over 3. Right, let's think about this. Sine of 30 degrees is a half. A half divided by 6 is 1 over 12. And when I times by 3 both sides, if I bring that over here, 3/12 are 1/4, and that equals sine of 150 degrees minus theta. Now, if I do inverse sine, oh, I have to put it back in degrees, so I should set up degrees, shift sine of 1/4. Right, so that means 150 degrees minus theta equals 14.477. Or it could very well be the ambiguous case, so it could be 180 minus that, so it could be 165.52. But this is clearly silly because then theta would have to be negative, so it's not that. So it looks like this. So 150 minus theta, if I add theta to both sides and do 150 minus that, then I will get theta is approximately 127.5 degrees. Yeah, moderately tricky. Let's see if I can make any sense of that. So 30 degrees is fairly short. Let's say I draw a line of length 3, and 30 degrees is an acute angle, like so. And the length from here to some other point is 6, so it's going to be fairly big, like that. Whoops, I said this was 30. Oops, looking like that. Yeah, it does look like this angle is going to be fairly obtuse, isn't it? Because you have to open it up quite wide. Yeah, 127.5 seems fairly realistic. Okay, well, that'll do. I've posted also a fair amount of vector stuff for you to be working on and through. And yeah, have fun.